guys, today I'm doing Khan Academy Global Winds and Currents.
One of my favorite things to do is go camping. For me, there's nothing better than getting outside, breathing in some fresh air, and taking a swim in my favorite river. Have you ever jumped into a river and felt that the deeper, cooler water closer to your feet was moving faster than the shallow, warmer water at your knees? That's a current, which is the word we use to describe how water, or even air, flows within a larger body of water, or air. But what causes a current? Well, let's start with the sun. The sun actually heats Earth unevenly. We know that it's hotter near the equator and it gets colder as you go towards the poles. Near the equator, the sun's rays hit Earth's surface more directly, while near the poles, the sun's rays hit Earth's surface less directly. In both regions, the same amount of solar energy is hitting Earth, but near the equator, this energy is concentrated into a smaller area, and near the poles, it's spread out over a larger area. So the regions near the equator get more solar energy, which makes them warmer, and the regions near the poles get less solar energy, which makes them cooler. This uneven heating of Earth also affects air pressure. Where it's cooler, near the poles, cool air will sink, making the air pressure high. But where it's warmer, near the equator, warm air will rise, resulting in low pressure. This is where the terms low pressure cells and high pressure cells come from. The low pressure, warmer air at the equator rises into the upper atmosphere where it cools and flows away towards higher latitudes, away from the equator. Because the air is now cooler, it starts to sink again and creates a high pressure band near these latitudes. This process repeats and creates a pattern of high and low pressure bands from the equator to the poles. We know that air flows from areas of high pressure to areas of low pressure. This creates air currents, or winds. Now, you might think that these winds would blow in straight lines from high to low pressure areas, but the global wind patterns, which we call prevailing winds, look like they curve to the right in the northern hemisphere and to the left in the southern hemisphere. This curving has to do with the rotation of Earth and is called the Coriolis effect. As these prevailing winds blow across the surface of the land and water, they also push against the surface of the ocean and produce wind-driven surface currents, which help to move ocean water. Here's what the global pattern of ocean surface currents looks like. Like wind currents, ocean surface currents are also curved due to the Coriolis effect. We can see that in these currents that are traveling north and south, which curve to the right in the northern hemisphere and to the left in the southern hemisphere. Together, as these surface currents of the ocean connect, they form giant rotating systems of ocean currents called gyres. The currents that drive these gyres extend from the surface to about 1 kilometer down into the ocean and help to move water all around the globe. But these gyres aren't just moving water, they're moving heat energy as well. Water is pretty good at holding onto heat it absorbs from the sun. So, as the water in our oceans moves around the world through this gyre circulation, the water also carries heat. Here, warm water generally moves from the equator to the poles, and cold water moves from the poles to the equator. But the ocean has other deeper currents that are affected by differences in temperature and density. Remember how we talked about areas heated directly and less directly by the sun, and how that results in low and high pressure areas? Same thing with water, except that water density is affected by both temperature and salinity, which is a measure of how salty the ocean is. Cooler and saltier water is more dense, so it tends to sink, just like cool air, whereas warmer and less salty water is less dense and tends to rise, just like warm air. So, with these deeper ocean currents, water actually moves vertically, or up and down. For example, water near the poles gets very cold. It also gets very salty because when sea ice is formed, the salt can't go into the ice. Instead, the salt stays behind in the water, and so the water gets saltier, or more saline. Together, the coldness and salinity makes the water very dense, causing it to sink deep into the ocean. In other parts of the ocean, wind drags deep water up to the surface in a process called upwelling. These vertical currents are connected by horizontal currents at the surface and in the deep ocean. Collectively, this system of currents is known as the overturning circulation. You might also hear it called the global ocean conveyor belt. So here's a map showing the overturning circulation. This map might look a little bit strange, but here we're looking at Earth from the South Pole. So Australia and the southern tips of Africa and South America are closest to the center of the map, while Europe, most of Asia, and North America are at the edges. Now, if you follow the currents in the overturning circulation, you can see that they flow all over the world's oceans, from the Southern Ocean around the South Pole to the Pacific, the Indian, and all the way into the North Atlantic. Like the currents in the gyre circulation, the currents in the overturning circulation also carry and disperse heat energy all around the world. Here I am, back in my favorite river, wading around and enjoying currents of cool water flowing around my feet. And even though this river is small, the currents that flow through it are similar to the global wind and ocean currents that flow all around the world. So these currents connect in our atmosphere and oceans, which means that we are all connected. So, currents connect us all.
Okay, next is reading. A current is a steady flow of fluid, such as air or water, within a larger body of that fluid. Prevailing winds are air currents that blow mainly in one direction. The global pattern of prevailing winds is caused by the uneven heating of Earth's surface. As prevailing wind blows across the ocean, they create surface currents in the water. Both prevailing and surface currents appear to curve due to Earth rotation. This is known as the Coriolis effect. Surface current connects to form large rotating systems called gyres. Gyres circulate heat around Earth by moving warm water from the equator to the pole. The ocean also contains deep currents that are driven by differences in density. Denser water, which is colder and saltier, sinks into the ocean. Less dense water, which is warmer and less salty, rises. The vertical currents are connected by the horizontal currents at the surface and in the deep ocean. Together, this is a system of currents. It's called the overturning effect. Let's go into the questions now. Let's go. What causes air current in the atmosphere? Ocean currents moving heat around. Sunlight heating Earth's surface unevenly. Ocean water is more dense when it is colder and more salty. Winds and ocean currents travel long distances around Earth, appeared in a curved rather than straight path. This is known as the Coriolis effect. What is the main cause of the Coriolis effect? Earth's spin on its axis? Yeah. How do ocean gyres redistribute heat around the Earth? They move warm water to the poles from the tropics. They move Okay. Next, lesson 4.
What's the weather usually like in the winter where you live? If you asked someone in Fairbanks, Alaska, they might describe below freezing days and navigating through huge drifts of snow. If you asked someone else in Miami, Florida, they might tell you that most days it was warm enough to go to the beach. How can two places on the same continent be so different? Well, it all comes down to regional climates. Climate is the long-term pattern of weather in a particular region. You can think of it as the average weather. A region's climate depends on many factors, including its latitude, elevation, and surrounding geographic features, such as oceans or mountains. Let's look at how regional climates depend on latitude first. Latitude refers to imaginary lines that measure how far north or south a place is from the equator, which equally divides the Earth in half. The equator is marked at 0 degrees latitude, and the mid-latitudes increase north or south until they reach the poles, which are marked at 90 degrees north and 90 degrees south. The sun heats the planet unevenly, so places at higher latitudes, which are farther from the equator, get less direct sunlight and solar energy on average, resulting in lower average annual temperatures. Places at lower latitudes, being closer to the equator, get more direct sunlight and solar energy on average, which results in higher average annual temperatures. This uneven heating creates a pattern of low and high air pressure bands from the equator to the poles, affecting the amount of precipitation that the different latitudes receive. In bands where moist air is rising, mainly at 0 degrees latitude and 60 degrees north and south, places experience a lot of rainfall, especially around the equator. In bands where dry air is sinking, like at the poles and 30 degrees north and south, places experience very little rainfall. This creates dry conditions at the cold poles, and desert conditions in regions near the 30-degree latitude lines. Another important influence on regional climates is elevation, or how high a place is above sea level. As air rises from lower to higher elevations, it expands and cools. That's why regions at higher elevations, like mountains, tend to have lower average air temperatures than regions at lower elevations.
Cool air goes to
Speaking
the
of
bottom.
mountains and seas, the presence of geographic features can also influence a region's climate. Let's start by diving into the impact of water first. Water heats and cools slowly, while land heats and cools quickly. As a result, temperature variations tend to be much smaller for cities near large bodies of water than for cities surrounded by land. For example, let's compare the yearly temperature ranges for Vancouver, which is close to Canada's Pacific coast, and Winnipeg, which is further east in the interior of the country. This line graph follows the average temperature in Celsius for each city throughout the months of the year. Vancouver starts out the year mildly chilly, temperatures rise a bit for a warmer summer, and then slope gradually back down. Overall, the city sees a pretty small range of temperatures throughout the year, because the nearby ocean influences the local climate as it gradually warms and cools. Compared to Vancouver, Winnipeg has a much colder winter, and a slightly hotter summer, resulting in a more dramatic range of temperatures throughout the year. We call a climate like Vancouver's a marine climate, and a climate like Winnipeg's a continental climate. Things get pretty interesting when we combine the impact of water with landforms. One unique example is a rain shadow, which can be found in places where mountains are relatively close to the ocean. For example, here's a satellite image of the Andes mountain range in South America. The mountains run north to south in this image, and they're close to the Pacific Ocean. Notice how the area between the Pacific and the Andes is green and lush, but the area behind the Andes is brown and dry. That's the rain shadow. What causes such a huge change? Well, when warm, moisture-rich air from the ocean meets the mountain, it's forced upward. As it rises, the air expands and cools, causing the moisture to condense and fall as precipitation. Now the air is much drier, which allows it to change temperature much faster. As that dry air descends down the other side of the mountain, it compresses and quickly becomes warmer, which leads to increased
Bye, that's all for today. Please like, subscribe, and hit the notification bell. Thank you for watching. Bye-bye.